Hello, everyone. Thank you all for coming this late. I know it's been a lot of great presentations, and I'm super happy that you managed to stay this late and come to mine. I'm happy you want to hear about search engines. It's something I really like to talk about. It's somewhat boring, but there's LLM, there's generative AI, so things get more interesting. For those who don't know me, I'm Zbyszko Papierski. I'm a search domain lead at Brainly. And I've been doing search for quite a long time. I mean, if I remember correctly, it's about like 12 years now. So I've seen a lot of stuff that happened to the whole search biz, if you will. One very important disclaimer, I am not a machine learning engineer. So if you see me talking about machine learning here and models and stuff, if you're going to ask me questions about this later, you will not get the response you want to. But we can try. I mean, it won't be good, but maybe it will be funny. What the search engineer does. There's this like whole iterative process where we analyze, our site has some search results we provide, you can query that site and get something back. What we do as a search engineers in general is we try to figure out what do you mean when you type phishing in the search bar. And we do this by employing very complicated and sophisticated mechanism you see here, which consists of offline process where we basically throw stuff around and see what sticks. And once we are more or less certain that something might help, we try this on production. It's sometimes not, so we get feedback from production and go back to the testing offline. It's obviously much more complicated than that, and I actually had a presentation, I think in this particular room, 2 years ago on JDD. That was called, At search you say sounds easy, right? Out of curiosity, who was at this presentation? Was there anybody here? That's great. Well, okay, I will not be repeating that one, but I'm mentioning this because if you want to understand how search engineering process works, that would be something I would go watch. I never did myself because I hate watching myself, but I recommend you do that. I was asked, not at this particular conference, but after doing this presentation, I was asked by a person, I think in Torun, do you think your work would change dramatically considering the rise of ChatGPT? If you don't remember, 2 years ago when I was doing this, and I was like, I've done this presentation for like 6 months or something, like on a few different places. And in the meantime, the third ChatGPT model came out, and whole world like basically gone crazy at this point. Like everybody was talking about how lifelike it is and so on. And for many people, that meant that there will be a tectonic shift when it comes to areas around providing content, basically stuff like searching, right? So obviously I was not really caught by surprise, but I couldn't answer it very well because that was just the beginning. So there is answer to this, obviously, and I will be giving one by the end of this. But first let's think about it. How do actually what's happening right now? The generative AI actually affects search. So, like I said, there is this notion that we will no longer be doing like textual input search. I will be talking stuff with our computer, right? So that didn't exactly happen. That was 2 years ago. And we are still working on this, and it's still a hype, and still, a lot of venture capitalist money is around. This is the thing right now, right? AI is everywhere. And it looks like it might actually change how we at least interact with our favorite sites. Google is introducing, the generative content in their searches with some ridiculous results sometimes. But that's happening. Right now it's happening. Things will happen for at least a few next years until we will switch to something else. And it does work, right? So for example, you can see who was the president of the United States when the war was ended. You can learn a new word, for example, for that meal before supper. It's merienda. And of course, you can solve the world hunger with ChatGPT. You can ask it what to do, and it will help. So yeah, there's you can at least find examples that this stuff works and actually can help you find things in an easier way than it was done previously because you interact with it naturally. And just to give a bit of a context to what we are actually talking about, there's a discipline of science called information retrieval that's actually about all of this. The definition is very simple. Information retrieval is the task of identifying and retrieving information that are relevant to the information need. And just to explain the last term, the term information need is desire to locate and obtain information to satisfy a need. Any need. I mean, you want to cook something, you need the recipe. You want to find the nearest hospital, you need the location, and stuff like that. So we've been doing things to solve this for a long time. Information retrieval itself as a branch of science is even older than text engines you all know. It's like, I don't remember the actual dates, but it's around 80s or even 70s. The first important approach, at least important in a way that we actually use it still, is full text search. And I will give you like a very crash course right now what the full text search is. It's a very rudimental here. It's a oversimplification, but it's sort of like, I want to give you a point how things differ between each other, just so you understand the limitations and the benefits of each. So who knows Apache Lucene? Okay, quite a few people. Apache Lucene is a very popular library that's used for full text search. What it basically does is break down documents into smaller pieces and allows you to match them with your query, and and it uses something called inverted index. It's a it's very simple structure. Basically, you have tokens. They come from the documents, and you have information when what are IDs of documents that contain those. So it's sort of like, that's the inverted part, right? So we have words that identify documents. We have document frequencies. We have more data here than those things here. For example, each entry on the posting list will also contain additional information about where the token is located in the document. But those things can be important. If you're like looking for a specific term that has like 2 words, you will be only satisfied if you find them close together. Like if you're looking for information retrieval, you're expecting to see those 2 terms close together, right? So those are the informations you can add here as well. Let's have an example how this indexing part works, like how do we actually add documents into the inverted index. Riding a bike in the middle of the winter. That's the document we want to index. We remove the unneeded parts, and we create a new document with a new ID, and we put it in the inverted index. That's the one. Sorry, first. So we added, actually that was supposed to be an animation, but it broke. We're adding those 20 to here, here, and here. If we want to search, we do a very similar thing. That's our query. We, again, break it down. And we do something very simple. We find exactly the same tokens. That gives us a list. It's here, and here, and here. What we do right now, we select only, again, too fast. We select only those that fit all of them, which of course is, again, animations broke, I don't know why, which is at document 20 we see here. So that was a query, and we got a question, answer from the index. The problem is that we don't really search for the meanings inside of those. I mean, we could search for a blog post about securing your bike for the winter rides, but we might as well find something that describes a novel where the hero rides a bike in the middle of winter. So there's a lack of semantic meaning to all of this, and full text search is really just a bag of words. You basically take a document which has like this, its meaning, and you reduce this to just tokens. That's it, and you don't really know what the token mean and how important they are to one another. So our quick trip through history of search takes us to what I call the first machine learning revolution. And this is very subjective. I mean, first from the perspective of search, so obviously machine learning was, and it's not really first like at all, machine learning was used for search for a long time, but one thing that really changed how we approach stuff, and it wasn't even that far ago because it was like 6 years ago, was a model, was a machine learning model called BERT. So it's bidirectional encoder representations from transformers, which sounds like a very forced acronym, to be honest. And BERT is a large language model, actually. We haven't used in a properly those terms before. BERT is a large language model, but it's not a generative one, so it behaves a little bit differently. It allows us to understand semantics of the particular document, of the particular sentence. How does it do that? BERT is trained in a very specific way. There are two steps to this learning, how BERT gains its insight. And one is called masked language modeling. First of all, before I show you the examples, BERT is trained on top of the Wikipedia articles. And the problem with training any kind of large model is that it's impossible to prepare a supervised set of data. Like basically, if we want to train some smaller model, we will provide it with training data. The training data will consist, okay, this is the correct matching and this is not. But in case of BERT, when it uses 3.35, I think, gigabytes of data, it's impossible to do something as effective because labeling a set like this will be practically impossible. And obviously, if we approach levels of GPT or Llama and so on, the sizes become even larger. So we have to have like an automated way of doing this without actual supervision over this. So BERT uses masked language modeling, which basically consists of training to taking the sentences and removing at random some parts of it. So in this case, we remove the bike, and basically we ask the model to predict what the word is. Once we do and obviously the whole mechanism, we do it as long as it can predict in a reasonable way what the words are. Another thing that is quite often used, but not always, is next sentence prediction, which means that we ask the model to predict which pairing makes sense. Like, for example, those are two sentences that make sense. They come from a single article, and those things are basically mixed. And you can do this without any supervision over this because you have just take the data out, like Wikipedia, for example. And what you do is that put it through automated process, which means you don't have to actually label the data, provide correct, incorrect examples. You can do it automatically, which changes a lot because you can train a very large models without human input. And it's important to be able to prepare something like this. So there's a process similar to searching. I see that animations are broken, so this one works. That's weird. How we use this for prediction or for search? We do it in the way that we break down those words into tokens. Again, that's almost the same thing. The difference here is that we are not removing anything. What we do now, then we have a dictionary of tokens basically for each model. Not all will be represented. Some might be marked as unknown. In this case, every of those is. And what we get from each sort of like sentence is we get the list of numbers basically, and they start with CLS and they end with pad. We can have more than a single sentence. We then add additional here, and then we finish with the pad. Once we have something like that, the list like that, we push it through the model. What we get when we push every token through the model, we get a list of vectors. This is basically a list of numbers that encode a meaning of each of those tokens, those numbers, into a representation that makes sense in the machine learning model. So basically, that means that each word is represented as a token in some form of space. And there's a way of comparing those vectors together. To be able to do this with sentences, we do something called pooling, and we create a single vector called embedding based on all of this. So what we got in the beginning was a sentence. In the end, we get a embedding of that sentence. And embedding is basically like a vector we can compare with other vectors that went through the same model. And to do this, we use something called semantic similarity. Semantic similarity is mostly used as a cosine of two vectors, which means we are basically calculating the distance between them. And the distance between them looks basically like this in the layman's terms. So you can imagine this as a difference. The distance between a woman and a man is the same in the given model as distance between queen and a king. So those models can actually encode semantics. They obviously saying that model understands something is going a bit too far, but at least it can encode meanings in relative terms, like presented here. And thanks to this, we can actually not only use tokens as in full text search to compare stuff around, but we can actually compare things in a way, in a semantic way. There's a lot to be said how it's being done. I don't want to overcomplicate this today. So that's how we do this. The process itself is used analysis. So basically, we analyze the sentence to get some information, and we find another content that matches the one we find. There's additional process I want to discuss here. It's called synthesis. And while from search we get information, we get some list of results. It's sort of like there's this last step you still have to do, right? So we found you the list of relevant information, and now do your research, right? So there's actually something quite useful for this. And this is where GenAI comes into play. So let's talk about second machine learning revolution. So like I said, BERT is also called LLM, a large language model, but its actual purpose is to provide you with those kinds of similarities, the way to sort of understand what sentences are about and how to compare them with each other. Just to make sure we understand this precisely, I will call this generative language models, large language models. And obviously, you know the great example, one is called GPT. There are others like Llama. We will actually be using Llama today. And how does training of model like that work differently? So first of all, if you think about masked language modeling, I mentioned before, it removes tokens from the middle of a sentence. There's this part of the name BERT starts from bidirectional, right? The reason why it's called bidirectional is that it can capture context of tokens both ways, going left and going right. And that's because it's trained this way. The way Llama is, for example, trained or other ones is quite different. This one focuses on a thing called next token prediction. And if you really think about this, ChatGPT or Llama is basically a smarter version of your your keyboards on your phone that tries to predict the next word you want to type. That's maybe not exactly the same thing, but similar thing. It's very smart. It's been trained on a lot of more data than those keyboards are, but it does something quite similar. The funny thing about next token prediction is that at some point while training the model and trying to use this, they came into a sort of a road bump, and this model didn't really produce any coherent content. What they were doing is basically having a sentence like this: "The sky is," and they want to get more, like the next token. So obviously they're going to select the most probable one, right? But it didn't work. For some reason, model was producing the same sentences over and over again. They made no sense. So there was something more that was needed to make this work a little bit better. What they did, and that's how those models work right now, is they added something called temperature. What it does, and the value can be changed, is it sort of like bumps the probabilities of top n tokens you have. So basically, there's this, and they randomize this. So this is, they select like few of those. With bigger temperatures, the lower ones are more probable to be selected, and they basically roll the dice. Each time, and while the answer might be actually the sky is blue, it might be that sky is lovely, for example. And it turned out once you start basically asking it to lie, it started to get creative, just like humans. And that's how those models works. Like, I mean, the difference of training is one thing, but there is way more. I mean, the Wikipedia is large. I mean, the text itself is like 3 terabytes of data, but the GPT-3 version, and obviously we had like few of those after those, were trained on much larger data sets, which sort of like has like some additional benefit to all this. I mentioned that BERT, because of its way of how it was trained, it can actually, it's better for guessing the context of the token, like being able to provide something that makes sense both left and right from the particular token. And since BERT is trained, GPT is trained, or Llama is trained basically forward thinking, like next token prediction, it might mean that for things like analysis, BERT is better. That's almost true, but thanks to the fact that GPT was trained on a much larger data, it can do a lot just by the sheer size of it, basically. But doesn't mean that it's not problematic. And obviously, by now, you probably know a lot of those issues because you stumble upon them every day. But let's recount them just for the completeness. First of all, I think that it cannot be understated. LLMs don't really know the truth. I mean, there's this thing that you quite often will hear about machine learning models in general, that they hallucinate. It's a word that it makes sense in some cases, but hallucination is not really what it is. I mean, since if the model doesn't know the truth and it was trained to mimic human speech patterns, it doesn't mean that it will provide you correct knowledge if it doesn't have it. The whole reason why we actually even can get a correct answer from GPT most of the times comes down to this guy. And Herbert Paul Grice was a philosopher. By the way, anybody study philosophy? No, okay. I asked this question in my previous presentation, and believe me, there were people who actually raised their hands. So just to make sure. So there's like, the one thing that he not really invented, but he observed when it comes to human interactions are the 3 maxims of Grice, or Gricean maxims. It's a maxim of quantity. When you ask a question of to someone, that person usually tries to answer that question with the correct number of information. If it somebody asks you information how to go to the main central station, you will not be recounting the history of a set central station, right? Most of us won't. The quality of this is basically, well, do not lie. If somebody asks you for directions, you provide them in the way that you think are truthful in most cases. A relation is a simple one. Relation means that you're answering the question somebody asked. So if somebody asks you a question how to get to the main central station, you are not answering them by telling them how to get to the airport. And last but not least is the maxim of manner, which means that you are matching the communication levels to your communicator. Basically, that means that you will provide the information in a way that the person asking can understand. And believe it or not, I mean, sometimes you won't, because internet can be a scary place, but most content you will find on the internet follows those rules in one way or the other. Obviously, we can understand them differently. But if on average, this will actually make this content make sense, because if we go to some forums, some pages, we want to provide information that fits those terms. Obviously, there are people who don't, and we call them trolls. But in most cases, that's the situation, and that makes the training data used for generative models in most cases quite okay, but it still doesn't mean that it won't create the content that doesn't make sense. By the way, those maxims are actually quite often used for evaluating the generative models. Basically, we ask questions and we tick the boxes of quality, quantity, quality, relation, and manner. That's the first thing. LLMs do not know the truth. Training a large language model is a huge and expensive task. That's why you won't be seeing a daily update of the model. Like, that's basically has all the current information. So you might find a model that actually makes sense. So if you're asking about something that is quite recent, in some case of some models, quite recent means like happened before last 2 years, you might get something that makes no sense. Another thing is that the information that LLMs can provide don't have to be actually very well sorted, as in a way that information might be okay, might be correct, but not really relevant, for example, to the season you currently are having or country you're in if you're trying to find something. So you can provide additional information, but you have to, like, as somebody who exposes a model to the user, you have to provide those information by yourself, because models have no way of actually getting them and using them for ranking the information they have and providing them in a correct and relevant way. And obviously the last thing is that there will simply be things that model cannot know about, because those are, for example, internal data. And hopefully nobody really leaked this online, and no generative model was actually trained on this. So how do we fix those issues? There's a lot of things said about this in the last few months, but I will only talk about the simplest thing I could find to get you in the subject of this. And this thing is goes through the notion that BERT is a great model for classification. The similarity thing that I talked about is a classifier, basically. And Llama or general generative models generate content and can summarize the data quite well. So let's use this. I'll be using something called retrieval augmented generation. It's not a new concept. I think that was like basically the first thing that came out when generative models started to gain traction. So some of you might be familiar with this. But just to make sure that we understand this the same way, let's explain the concept in simple terms. Imagine you're asking a question to the model. What happens in retrieval augmented generation is that we use the same question that you just asked to to encode the embedding, like we discussed before, and we asked a separate vector database that contains some truthful information, like it was based on the Wikipedia or was based on some books and so on. And we find additional results. So we basically do a search underneath, like actual. We use the query, we put it in the search engine. It doesn't have to be vector database. We'll be using this for example, but any search engine will do. We retrieve the results, and with both the question and some prompt and additional context that comes from those results, we create an enhanced prompt. Sorry, I was pointing to somebody. We are creating an enhanced prompt to the model, and we get our answer. The idea here is that it doesn't really have to use the knowledge that's inside the model, but we can actually provide it an external source that is better for classification, because it uses like full-text search engines or vector databases with BERT. We add additional things. And thanks to this, we should be getting more results, and mainly truthful ones, which is quite important. So I want to show you a quick example how to do this. And since it's a Java conference, I'll be showing some Java code, just like to quickly whip up something that works. Let's discuss what we will be using. First of all, I will be using OpenSearch with the KNN plugin. OpenSearch is a fork of Elasticsearch, which itself, both of them use Lucene underneath. KNN it stands for K nearest neighbors. It's a way of using vectors to retrieve the most similar content, basically. So that's the realization of the model in a way that actually works for search. There are multiple things you can use. For this, I only use OpenSearch because A, I know it, and B, you can tie both KNN, which means vector database, with the actual full-text search, and you can tie it all together, use this together. The same thing will work for Elasticsearch, which has the similar, not the same, but similar plugins. So if that's your poison, go ahead. But you can use anything that's provided. That's fine. As you probably know, there are so-called open source models out there you can basically deploy on your laptop and use this. The air quotes were because those aren't really open source because none of the companies that releases them actually release the training data, and that would make it open source. Obviously, they're not doing this because there's a storm of lawsuits coming in and based on this, and they will not be jeopardizing this. But you can still use this in any way you want, and you can easily deploy something like Llama 8B model on your laptop. I mean, I will be doing this here. I talked a lot about BERT, which is funny because I will not be using it. I'll be using a thing called mini-LM. BERT is a obviously smaller model than Llama, but it's still quite large. And there's this process of learning models that's called distillation. And what it means is that you can take a big model like BERT, and based on the results that BERT provides, you can train a smaller model that will not be better than the original one, but will be good enough, and will be much smaller to begin with and much cheaper because of it. So we'll be using mini-LM. And we'll be using a library called LangChain4j. They don't have a logo. This is actually originally a Python library. Its Python version is much more advanced than the Java version, but honestly, I hate Python, so I will not be showing Python. And this is a Java conference, so gives me a good excuse. And that's it. Let me show you how this works. This is a live demo part, so obviously stuff will not work correctly. So let's see. First of all, I want to explain you how we actually are doing this. Let me get here. This is what you see as a code, LangChain4j code, and it sort of like demonstrates all the concepts I was talking about before. What you need to do is you need to have an index of data. In this case, I created a small program that gets PDFs from the library and indexes them into the embedding store. And you can do this easily in LangChain. It provides you out-of-the-box solutions that you can use. Some integrations that are already there, like OpenSearch embedding store. And it's actually quite easy to use because what you just need to do is to have this embedding store open, pointing to your OpenSearch. There's a function called load documents that you can use Apache Tika, which is a very cool way of analyzing almost every format I know. So we don't even have to think about what format is being used there. And one thing you have to do, and I haven't talked about it well enough, is that if you have like a PDF or even multiple PDFs, you cannot just index all of it in a single document. It's like pages upon pages because none of the models will work in this and actually provide you useful information. And prompts you'll be creating with documents this large will make no sense. So what we need to do is we need to split the document into smaller parts. And to do this, there are multiple ways. The best one currently, or at least at the time I was writing this, is called the recursive one. It sort of tries to split it by sentences and create segments that should make sense in terms like how big they are. There are different ones available here as well. For example, you can just cut it in like basically smaller halves, smaller parts without looking into anything. And LangChain Python version actually has a splitter that can use a machine learning model to extract paragraphs that really make sense from the perspective of a human. When I was writing this, Java version didn't have this, but LangChain for JS is still a new port, and I'm guessing they will import this at some point. So it's quite possible, but by now it's already there. So look for it. For now, we will this recursive splitter, and then we create embeddings for all of those segments. We just split. We're using this by using embedding model. We provided one here because we are going to be using one for search as well, because if we are searching in the embedding store, we need to have embeddings for both the documents and the query, obviously. So the one I provided here is one more, all mini LM, some version of it at least, that was supposed to work well for different languages. So this initialized books, like I showed you, basically creates the embeddings and embeds them and adds them to the embedding store. Sorry for the quality of the code. I'm a manager. Once we have those where they supposed to be, we need to have a way of retrieving them, and this is what embedding store content retriever does. And it uses a store we could just created. It uses the same embedding model. That's the thing. Embedding models for query and for the documents in the index have to match. And we tell him how many results are we expecting and what's the minimal score. The score for the documents goes from -1 to 1. We are obviously only interested in the closest it is, the closer to 1 it is. So 0.7 is like some value I just came up with. Next, what we want to do is to be able to actually use a streaming model. We want to use the model, the generative model. I'm using Ollama. Ollama is a tool that allows you to run quickly open source models or available models. It can run Llama models as well, but it can run ones too. We'll be using a Llama 3 latest. This is also actually an alias to the 8B model I talked about before. And this is basically a timeout. As you probably all know, it can take quite some time to wait for results. This is a CPU-only solution because my laptop cannot do better. But still, the fact you can run this from something like this, I think is amazing. It's some hack here so you can see the content we'll be getting from the embedding store as well. And here, where the fun around tying this all together comes forth. There's this called retrieval augmenter. We have to provide a specific prompt template. And this one is, we have provided context below. Context is added here. That's how content injection works. Given this information, please answer the question, and user message is another one of those template parameters, and so on and so forth. You don't actually have to do this. There's one provided by default, but I wanted to show you how does this work under the hood. And then we create, using something called AI services, we build a streaming chat. Streaming chat is a class I created. If you want to, streaming is there are two ways of doing this. There's a regular one and there's a streaming one. Regular one will wait until the model has a whole answer to return, but as you all know, it can take quite some time. So I'm using a streaming version that allows me to print each token as it comes in. Remember that training part, next token prediction, the models, what they actually do is they print out the next token, and then the next one, and then the next one. That's how they work. They do not provide the whole answer at one time. They will, based on the original content and tokens it already created, create another one. And somehow it actually can answer something that makes sense. That's simply amazing. So we have something like this. Let's show you how this works. Just a quick thing. We have time. What I'll be using here is a paper, and okay. I don't know, I'm not sure if this will work. Okay, here we go. So paper is called PAL, Program-Aided Language Models. I told you that RAG was the first thing that basically came out, but that wasn't the last thing that came out. One of the additional things that people figure out that how to aid the model, the large language models with, is called Program-Aided Language. It can help with calculation tasks. You probably all know that GPT is famously lousy with mathematics, for example. What program-aided language models do is we ask model to generate the program that solves the problem. We run the program by ourselves and then use the output of that program to as a part of the content, and then we go with that content to the prompt and generate the message. I will not be talking about this, but I wanted to show you a quick difference between using RAG and not using this. So I have the model already running, and let me show you, let me ask him a question. You probably are not seeing none of this. Okay. Is this, can you see? Let me make it even bigger. Okay, what is PAL in LLM? This is a pure llama model, nothing else. It will not be using any kind of additional input. I'm seriously wondering what it will generate this time, because in most cases it generated me very, very different things. Yeah, that's not true. Let's stop it before it embarrasses itself more. Actually, I got very interesting stuff around this. If you read through this, it looks really reasonable. I'm not sure what it wrote this time. Each time I got this, I got a different response. Each time sounded like an excerpt from basically a science book or something, and each one was wrong. Like every single time, it would make no sense. The reason is actually quite clear, that because model was trained with the data that's like at least 1 or more years old, and PAL is relatively new. It cannot know anything about this because it was never in the model. But let's see if our mechanisms is actually smarter. By the way, this repo is online on GitHub. There are some things I will have to commit, but there are way more examples of different mechanisms if you want to see. There's even a PAL example here. But let's ask the question: what is PAL in LLM? We got a lot of text. Those paragraphs are quite big. In some cases, they might make no sense because we are looking for a very simple thing, and we don't want to return those results to the user because, like I said, they can make no sense in context of the question. But they provide the content and use this, and like I see, they actually did. Here's a cutoff line. Based on provided context, PAL, programming language, is a technique that leverages language models to generate intermediate steps in programming tasks, blah, 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 blah. That's correct. Let's ask some more questions. That is not correct, or at least it's definitely not something I wanted to get from this. Which might sound weird because I'm providing all the content that you want here, and obviously the document, if you look through the paper itself, contains the information how to simply implement PAL and use this in Python actually, so maybe that's why it doesn't work, because Python is, anyway. So just using this is not enough. And there are ways of actually dealing with this. Even with the same data we have right now, we can optimize our search engine in a way that actually can answer those questions. But the thing about this is a process. I mean, what happens below all of this, the results that you're seeing here are search results. So while we have a fun tooling that allows us to, mess around with something, provide something better than the original experience, we still have to work on the stuff that's underneath. We still need to work work with the search engine that we use. So it's not really done. The question that was asked me all those 2 years ago Do you think that your work will dramatically change considering the rise of ChatGPT? It took me some time to get my footing all around this and actually work with those tooling. We use RAG in our day-to-day work. We can use it quite effectively, and we are using content that's not very well structured, so we have mechanisms that do paragraph extractions very, very well. And this can be done, and it requires the same process I described before, the analysis, the offline testing, finding new ways of actually getting the information. The way of serving this information changed, and will probably change more in the future. But the work itself, it didn't really. Thank you all for paying attention today, and